Hello everyone, welcome back. So in the last lecture we were talking about LSPR resonances. So in this lecture I want to talk about what is known as surface plasmon polariton. We also call them as SPP. So if you go back in the first lecture of the week, I talked about transverse and longitudinal waves, right? We said that there are these two categories wherein you have transverse waves and then longitudinal waves. Longitudinal waves essentially give you bulk plasmon is what we mentioned, and we said we will not really talk about that much. In case of transverse waves, that means wherever the electric field is perpendicular to the direction of propagation, you can have two types of resonances. The first one is LSPR, localized surface plasmon resonance, which we talked about in the last 1.5 hours or so. The other type is what is known as surface plasmon polariton. Essentially, a polariton means it's a propagating wave. Okay, so it's a coupling of surface plasmon and electromagnetic waves. So that's why we call it surface plasmon polariton. Similarly, when you have coupling of phonon and electromagnetic wave, you have a phonon polariton, okay, and so on. So why are these interesting? Well, it turns out that essentially the surface plasmon polaritons, SPPs, are essentially charge oscillations at the interface between a metal and a dielectric. Okay, for example, here this is a gold film and there is air on top, let's say, and then on the surface you can have these charge oscillations which can propagate on the surface. Okay, and this is useful because let's say you can think of a waveguide. For example, you have a wire which carries electrical signal, and then you have a waveguide which carries optical signal. It turns out that using a surface plasmon polariton, you can create a waveguide for the plasmon. So for example, this is, I have a waveguide which is going like this, and then I can excite a surface plasmon on this, and then the surface plasmon will propagate on the waveguide. And this is very, very useful because we can use it for on-chip communication. It's potentially one of the ways by which you can combine electric signals and optical signals. Okay, that's why there's a lot of interest in this. And this has been, this has received a lot of attention in the last 2 decades. Okay. So in this particular lecture, we will, in the next and also the couple of subsequent lectures, we will understand how the surface plasmon polariton behaves. Okay. And we will talk about what are the advantages once again. So to get started, let's consider what happens when light is incident on a metal and a dielectric interface. Okay. So dielectric, of course, we know that it is, the permittivity is greater than 0. It's positive number. And okay, by the way, yeah, I have given a symbol of epsilon 1 here, but I'll try to follow a different convention so that you don't get confused, because we said epsilon 1 is real part and epsilon 2 is imaginary part, right, in the past. So let's try to denote dielectric by epsilon D, and let's denote the metal by epsilon M. Okay. So now you have this interface between dielectric and metal, and the coordinate axes are this. So you have the x and y plane, and the x, y. So in the z is the direction of incidence. So you have a wave which is incident from the top in the negative z direction. So what will happen? Okay. Intuitively you might understand, let's say if you have a mirror, you understand that that's a metal film which is reflecting a lot of light. But we'll try to go a little bit deeper than that. Okay, why that is happening. So if I consider my wave which is incident in the negative z direction, and y is out of plane, it is essentially uniform in that there's no variation, so you can just ignore that. So essentially it's a z and xz plane problem. Okay, so when I have wave incident, I can denote the wave vector of the first medium, which is, let's say, dielectric kd, I'll call this. Essentially I can write it as a vector. So essentially I have, there's an x component kx, there's a 0, and now there is a z component of the wave vector in the so it's propagating in the negative z direction, so I'm writing as a minus kz. Okay, this is a k dielectric. And now I can also think of a k metal, which is basically the wave vector in the metal. Now because this is the tangential component of the wave vector has to be conserved, so we can write it as kx 0, and now there is a negative kz. Okay, or if you want to make it more explicit, I can write it as k2z and k1z. Okay, denoting the wave vectors in those materials. And we have seen from the analysis of the dispersion relation that we can write the entire sum, right? For example, in the medium 1, or let me take the case of medium 2, that is much more interesting. So let me say in the medium 2, that is my metal, and medium 1 is a dielectric. Okay, so I'll write it as kx square plus k2x square, k2z, sorry, it's not k2x, k2z square should be equal to, the dispersion relation tells us that k square is omega square by c square, right? So there should be an omega square by c square. And then there is also, this medium has a certain refractive index, so there will be an n square. This is the dispersion relation we studied. So now this I'll try to rearrange a little bit, and I'll write it as, since we know that this is a non-magnetic medium, mu relative permeability is 1. So I'll simply write it as n square, I'll write it as epsilon metal k naught square. Okay. Now the interesting thing is, there are a range of frequencies where the metal has a negative permittivity. So what happens if your epsilon metal is negative? Okay. So what we will try to look at is k2z square should be equal to epsilon metal naught square minus kx square. Let's assume for a moment that there is this wave that propagates on the interface. So kx is some positive number. Okay. And my epsilon is negative. So overall, this kz is a negative number, kz square. What does it imply? It implies that my k2z is imaginary. What does it mean that k2z is imaginary? Well, we saw how the wave propagates, right? If you have an imaginary wave vector, immediately you have an attenuating wave or an evanescent wave, right? So that means that if you have a wave incident on the metal dielectric interface, the light cannot penetrate into the metal. Okay. So this implies essentially light okay. So what happens if you don't if it doesn't penetrate? Well, the only way to go is back. So it gets reflected. This implies that light is okay. How much light is reflected? That depends on the loss in the metal. If your metal is lossy, then some amount of the light is absorbed within the metal and rest of it is reflected. But if you take a low loss metal, like let's say silver, you will see that most of the light gets reflected. Okay. And that is what I'm showing you here. So this is the calculated reflection from metal films of different thicknesses. So what you see is that as I have, let's say, thickness of 1 micron or 100 nanometers, I get a significant amount of energy which is getting reflected. But if I go to a thin metal, I don't see that. Okay. But why is it getting reflected? Well, this idea of metal has to have negative permittivity, right? When will metal have negative permittivity? So if you look back in the Drude model, epsilon metal is basically, in ideal case, omega p square divided by omega square. So if my frequency is smaller than the plasma frequency, then I'll see that my metal has negative permittivity. So I can plot out my metal's permittivity. Let's say I'll call this an omega p. At plasma frequency, my permittivity is going to be 0. And below plasma frequency, your permittivity is negative, and above it goes to a limiting value of 1. That's the behavior of a Drude metal. So when you have metal which is permittivity, basically epsilon metal of I'll only talk about the real part. Let's call me prime. Epsilon metal prime is less than 0 for omega less than omega p, or lambda greater than lambda p. So above the plasma frequency, if in terms of wavelengths I talk about, the frequency corresponding to the plasma frequency is here. In this case of silver, this is about the plasma frequency, this omega p, or rather lambda p if you want to call it. Okay, the plasma frequency wavelength. Plasma wavelength, let's say, I don't know. So above that frequency, I see that my metal is negative. That is why it is getting reflected. Okay. And below that, it behaves like a dielectric, and there is a certain amount of dielectric constant that we can use to compute. And that's what, you have some reflection that's happening. Okay. So now this is how metal behaves. And if you go below, let's say 10 nanometers, around 10 nanometers film, basically you have tunneling, tunneling of electromagnetic radiation of EM wave. So you have the attenuation that is happening, but before it can fully get attenuated, some of it is actually coming to second interface and it's propagating. So we say that we have a tunneling process, and that is basically causing the light to be reflected. So this is important, we'll come back to this. But if you look at it, it seems like there is nothing interesting going on. It's simply going to get reflected. But where is the question of this Plasmon Polariton that I'm talking about? All right. To understand that, we'll have to do a little bit of mathematics. Okay. So this is very, it's not that complicated. It's sufficient if you understand the final result, but I think it's important for us to go through it once. That's why I would actually go through the procedure for derivation. Okay. So now the excitation of this surface waves at the interface of metal and dielectric depend on the type of wave that is incident. Okay. So what happens is the response depends on whether one, we have a transverse magnetic wave. Okay. Whether we have transverse magnetic wave or transverse electric. The response is going to be different for both cases. Okay. So we call them as TM and TE. What does it mean, TM? Well, it means that, we talked about this metal dielectric interface. If I just put that one more time here. So you have the epsilon metal and then epsilon dielectric. And if I call this as medium 1 and medium 2, you have a wave incident. So I said this is my X direction, this is my Z direction. So out of plane is my Y direction. So this is my Y direction. So transverse magnetic means your magnetic field H is going to be having only the Y component, Y cap. Okay, there is no other component. There is no X and Z component of the magnetic field. That's why it's transverse. Transverse to the plane of incidence, in this case of the metal dielectric interface. Okay. So now you can, if you have transverse electric, the electric field exhibits that property. So you have only EY term. There is no EX and EZ term, but only EY term. Okay. So when you have such a scenario, you can say that the wave is actually having, the transverse magnetic wave can excite the Plasmon Polariton. So we'll consider that. So how do we show that it actually is a Plasmon Polariton? To show that, I'll assume that, let me say, my magnetic field, right? I'll first only take the Y component. So H1Y, electric field, the magnetic field in the Y direction in the first medium. I'll say that I can write it in terms of this expression, H1 exponential I k x x exponential minus kz k1z z. What does it mean? What is this expression? It essentially means that you have a plane wave which is propagating in the x direction. So my exponential ikx is my plane wave propagating in x direction. In addition, you have an evanescent component which is essentially the z component. So this exponential minus ik1zz is the evanescent wave in z direction. So what it essentially represents is my electromagnetic wave which is decaying in the z direction here, and it is propagating along the interface. Okay, I'm just assuming it, and I'll eventually show that there's a certain condition that has to be met for this kind of a wave to exist. Okay, that's how I'm going to prove that. Okay, similarly, I can write out an expression for H2 of Y, which is going to be some magnetic field amplitude, and then exponential ikx and x. Note, I'm just using the same plane wave because the tangential component of the wave vector has to be continuous. So I'm taking that. But now I'll say that I'm actually, this z equal to 0 is my interface here. And below is metal, above is dielectric. So what I'll say is, I'll take an exponential, because z is negative in this sense. So k2z and negative z. So again, because z is negative, this second component is a evanescent. This is also an evanescent component. And there's a plane wave, which is there. So effectively, I have a wave which is only propagating in the interface. So both sides, if you look at the magnetic field, above and below the interface, it's going to be decaying. Okay. This is essentially my assumption. Okay. This entire thing. Okay. This is an assumption that such a wave exists. Okay. But what does it mean? Well, we already talked about the propagation constant, right? And essentially the propagation constant in the z direction is imaginary. Okay, let me write it out. Okay, let me take a case of k. Instead of writing it in 1 and 2, I'll say that k jz, simply j equal to 1 or 2, okay, is going to be kx square minus epsilon. Okay. Yeah, it's metal or dielectric, so simply I'm just going back to the notation, changing the notation slightly, and whole root. Okay. So let's consider a case. What happens? This kjz is essentially the attenuation constant. J is either 1 or 2. What does it mean? If I take, let's say, a case of epsilon 1 or epsilon dielectric equal to 1, epsilon metal equal to -1, what will happen? Okay. So if you put a dielectric, and let's assume for a moment that such a wave exists and kx is greater than k0. Okay. Okay. And also let which actually will turn out to be true. Okay. The propagation constant along the interface is actually greater than k0. If I have a scenario, then I can compute what is my k2z and k1z. Okay. And if you put in, because this is dielectric, right? This is going to be, if it's dielectric, my k2z is going to be smaller. But if you have a metal, this negative and negative, it essentially adds up. So if you do this, essentially you will see that k2z is greater than k1z. So this means that wave decays faster in metal. That's it. Okay. So that's it. I mean, we have not really done any derivation or anything so far. We just said that such a wave exists and this is the property. Okay. Now, how do we actually understand that? Okay. To understand what happens, again, one more small thing. Everything goes back to the Maxwell's equations. So we'll just compute electric fields. So far we have assumed magnetic field. So if such a magnetic field exists, what will be the electric field? And for that, what we will do is, we will start from the Maxwell's equations, the Ampere's law. Curl of H is essentially, we know that it is mu naught of J plus first derivative, time derivative of the D, displacement field. And in this case, we are not taking any sources or anything, no currents. So this is 0. Okay. And if you take the first derivative, let's say if you have a plane wave, right, of a monochromatic plane wave, you will see that if you take the time derivative, it's an exponential minus I omega t dependence. That's what we have assumed for plane waves. So if you do that, essentially dou d by dou t will be minus I omega epsilon E. Okay. Right. So because, time derivative is exponential, time dependence is exponential minus I omega t. So if I take a derivative, I'll get minus I omega and d is epsilon times E. So that's what it is. Okay. So now, and also, for a moment, what did we assume? H1, let's say if I take Y, that is going to be H1 exponential IKX in the X direction and exponential minus K1Z Z. This is my dependence that we have assumed in the first medium. So what is going to be curl H now? Curl H, I can simply write out the cross product. So you have X cap, Y cap, Z cap, and you have dou by dou X, dou by dou Y, and dou by dou Z. And now the Z, the magnetic field, I'm assuming it to be only in the HY direction. So this is going to be this, only this component. And that entire thing is going to be equal to minus I omega epsilon times E. Okay. If we do that, let's see what happens. So, you can write out the individual equations. So what can you write? So if I take the X component, will there be an X component? Well, there will be an X component, and that is going to be dou HY by dou Z in the x component, and then will there be y component? Well, no. In the z component will be plus dou hy by dou x, right? That is equal to, this is the z component, that is equal to I omega. This is the first medium, so dielectric electric field E. Okay. So this is my electric field. That's it. Okay. So how do I solve for this? Well, first let me first do. Okay, let me take the derivative first. So I'll take the z derivative. So I'll get kz. Minus is there. So k1z dou hy by dou z. Sorry, that's not required. K1z. I'm taking only the z derivative. I'll simply call it h1y x cap. And then x derivative is again plus. So plus, now this ikx. So ikx h1y z cap, that should be equal to I omega epsilon d E1. Okay. The electric field in the metal, first medium. So what happens now? Well, I can rearrange the terms. Okay, so basically I can multiply, or rather there's a positive term, okay, and then I can turn it this side and then divide. If I, let's say, take the product of minus I, okay, if I take the minus I, omega epsilon d E1 is going to be minus I k1z h1y x cap plus, no, this is minus I, so then minus of minus, so plus it becomes, okay, let me, am I doing it right? So there's an I omega, there's a minus I omega, sorry, yeah, so that's where I made a mistake here. Yeah, see, there's a minus here, there should be a minus here. If there's a minus, so instead of multiplying by a minus I, I'll multiply by a I. So then this is going to be ikx. There's a minus here, see, lot of mistakes in algebra, all right. So I'm multiplying only by I. So now this is going to be minus kx h1y, okay, and z cap. So these two terms, dou hy by dou z, so minus kz, k1z, h1y. So there's a minus and there's a minus, so this should be plus. Okay. I think this should, what it should be. If I do this, this is what it should be. Minus kx, h1y. Okay. All right. So basically what it tells us is my E1 is going to be h1y, I'll take out common, divided by epsilon d omega into ik1z x cap minus kx z cap. Okay. And similarly, I mean, I'm simply replacing by metal by dielectric, sorry, dielectric by metal. So I'll write out the electric field, it will follow the same fashion. H2y, or rather, H2y divided by epsilon metal omega. And the only difference is, now kz is going to be negative because it's a negative z. So minus ik2z x cap minus kx z cap. This is my electric field. So what is the one of the important features that I want you to recognize is that we started out with the magnetic field in the y direction, but if you look at the electric fields, it's only in the x and z directions. Okay, that's a nice feature. So basically what happens is your combination of hy, ex and ez are essentially solutions for Tm. Okay, for TE, you will have solutions of the form EY, HX, HZ. So this is going to be my TE solution. Okay. So Tm is only this HY, EX and EZ. This is a nice symmetry in the Maxwell's equation that comes out. All right. And so now you have this H and E terms, right? The fields. So we want to understand what is the implication of that. So for that, now if I say that H1Y, right? H1Y, the magnetic field, it has to be continuous across the interface. So H1y at z equal to 0 should be equal to H2y at z equal to 0. Okay. So if I put Z equal to 0 in this expression, I'll see that this implies H1 equal to H2. Similarly, why is this? Because the magnetic field has to be continuous. The tangential component has to be continuous. Similarly, your E parallel has to be continuous. What does it mean? Well, your electric field has to be the tangential component. So the Z is a normal component, so we don't need to worry about that. But the tangential component has to be continuous. That means that, there is an I here, there's a minus, there's K1Z, K2Z. So let me simply, I'll remove the omega parts. I'll write only in terms of K1Z. Okay. So this is going to be K1Z divided by epsilon dielectric should be equal to minus K2Z divided by epsilon metal. Okay. So it finally implies that my K1Z divided by K2Z should be equal to minus epsilon metal. Epsilon 1 is dielectric anyway. Dielectric, and this is epsilon metal. So what it means is that the propagation constant have to be in this form. Okay. So we'll just take a few minutes to understand what are the implications of this. This is one expression that I need you to sort of analyze. Okay. So I'll just mention it one more time. So what I'm saying is K1Z divided by K2Z is going to be equal to minus epsilon dielectric divided by epsilon metal. This relation has to hold, only then you have a surface wave. Okay. Has to be true for surface wave to exist. What does it mean? It essentially, K1Z is a K2Z, both are real positive numbers. Okay, these are propagation attenuation constants, right? These are both positive. So this means that epsilon dielectric and epsilon metal have to, epsilon metal must have opposite signs. This is one of the conditions for the plasmon to exist, surface plasmon polariton to exist. If not, it won't work out. Okay. That's why we need a metal and a dielectric interface, and surface plasmon polariton can exist wherever the epsilon is negative for the metal. Okay. And so basically what I have is K1Z now. So if I go a little bit further, so I already understand my K1Z square should be equal to Kx square minus epsilon dielectric K0 square. Similarly, K2Z square is equal to Kx square minus epsilon metal K0 square. Okay. I can combine both of these and eliminate. Okay. So combine and eliminate K1Z and K2Z. Because we know what is K1Z, K2Z relation, right? You can easily compute that. I mean, this is simple algebra. What you will end up getting is Kx square equal to epsilon dielectric, epsilon metal divided by epsilon dielectric plus epsilon metal, K0 square. So what this means is, if you have such a interface between a metal and dielectric, these waves can exist, and the propagation constant of that wave is going to be given by this relation. So this is the what is known as dispersion relation for SPP, surface plasmon polariton. Okay. How is that behaving? Well, in a nutshell, what is happening is, let's consider when, if you immediately, whenever you see a sum in the denominator, we should immediately think of what happens when the denominator goes to 0. So let's say what happens if epsilon d plus epsilon metal equal to 0. Can that be 0? Well, it can be. It simply means that epsilon metal equal to minus epsilon dielectric. If I assume air, which is 1, my epsilon metal has to be minus 1. And epsilon metal is simply 1 minus omega p square divided by omega square. Okay. So that means that minus 1, right? This is, sorry. Yeah. So basically omega equal to omega p divided by root 2. Whenever my frequency is equal to omega p divided by root 2. This is surface plasmon polariton resonance frequency. This is surface plasmon polariton frequency. Whenever your omega is equal to that, omega plasma frequency by root 2, you have this resonance excited. And what happens when you have such a resonance? I'll discuss it in the next video. But briefly, what happens is, we talked about the dispersion previously. So kx omega versus k relation. And we know the light line which essentially captures the omega equal to ck, right? Now, when you see that this combination is going to be higher, greater than 1, okay? Especially for frequencies less than plasma frequency, you'll see that for frequencies less than plasma frequencies, you'll see that the dispersion turns out to be of this form, okay? Essentially your kx is going to blow up when your frequency is going to be, if this is my omega p, at omega p by root 2, my kx is going to become very large. That is my plasma frequency. That's a SPP frequency, resonance frequency. Now, what happens at this resonance frequency and what happens below and above and all that, we will consider in the next lecture. So, I'll see you there. All right. So, this is the mathematical part of it. In the next video, I'll essentially talk about the intuitive part. All right, of what a plasmon frequency means, SPP means, and so on. All right. So, with that, I'll stop. I'll see you guys in the next lecture. Thank you so much. Bye.